Today we're going to look at the Pevono PS305H. This is a variable bench power supply. It will deliver from 0 to 30 volts and 0 to 5 amps. We're going to put this thing through tests. We're going to load it up. We're going to take it apart and see how well this thing's built, and we'll let you guys see inside how well it's constructed. And this one's not perfect, but we'll take a look. So we power the unit up. And the first thing we see is it's got two 4-digit displays, one displaying the voltage and one displaying the current. And we have two adjustment controls on here. We can go right from 0.00 volts, and with the fine control, we can start down. So if we need really low voltage, we can turn it right down to, well, I guess in theory, you could start out at 0.1 volts. Can I get it to 0.1? I can get it to 0.1. I can't get it quite to 0.09. Not that you'd ever need voltage that low. But if I turn up the current, I'll crank up the current here. If I short my leads together, we're drawing about a half an amp at 0.06 volts. I'm dead shorting the leads here. So yes, it will control down to a very low voltage. As we turn up the voltage here, this is our course control. We also have to have some type of a current allowed, or we're not going to get any voltage at all, right? Because if we've got everything turned down to 0, we probably won't see anything here on the voltage control. So you can have the current turned down to 0, or you're not going to get anything. So you have to set some type of a current. So just turn the current up a little bit, and then you can set your voltage. Normally you'd set your course voltage about halfway up, and then you dial in, or your fine voltage about halfway up, and then you can dial in your voltage. So if you want 13.8 volts, for example, set it in the ballpark, and then use the fine adjustment to set your voltage to 13.8. which is your average voltage for running car accessories, for example. Now, what I'm going to I'm going to basically overload this thing and see I'll show you what I'm going to try and power up with this thing. First, we'll check the voltage and see how accurate it is on the Dr. Meter voltmeter here, set to DC voltage. The meter says it's putting out 13.8, and according to Dr. Meter, it's putting out 13.7. But we'll bring in the fluke and see what the fluke says. Because, if it's accurate, it'll be a fluke, right? Or is the saying, it'll be a fluke if it's accurate. And, well, now we have two discrepancies. We have the Dr. Meter saying 13.7, and we have the fluke saying 13.9. And the meter says 13.8. We're in the ballpark. We're splitting hairs here, but I'll take the meter as being accurate. So maybe both of these meters are slightly off. Now, in case you guys are wondering what I'm going to try and power up, I have a work light. This is a 12 volt work light. Hence the black and red power cord. That is a 35 watt xenon lamp, like you find on a car. Actually, that's what it is. It's a car headlight. I'm going to have to turn the current all the way up on this thing, because this thing's going to draw a heck of a lot of power. It's going to draw a lot more than 5 amps to start this thing up. Guaranteed. I don't have a power supply that's powerful enough to start this. I have to actually run it off a battery, because it draws closer to about 8 amps when it starts. But let's just see if this thing will actually start it up. Okay, it's flickering a bit, but I have a feeling that maybe once the lamp strikes, it will settle down, because it should drop down to about 4 amps once this thing gets going. But to actually get it going, it takes a lot of juice to get this thing going. And you can see, if you look on the meter here, I don't know if you guys can read it or not, but it's drawing, there we go, it was drawing almost over 6 amps there. But now that it's going at 13.8 volts, this thing is drawing 2.9 amps. To give you an idea how bright this silly light is, well, it's a 35 watt metal halide type, basically, bulb. It's an arc lamp. You can see the little bulb there. This is what's in cars. This actually came out of my car. When I got my car, it had these lights in it, and they're these ridiculously blue looking lights. You can see how blue it is there. And I absolutely hate these lights on cars. I don't know, people must think they look cool because they're bluish. This is 6,000 Kelvin. And I'm still running the same type of lights. I just changed the bulbs down to 4100 because, believe it or not, you can't see as well in the dark on a wet night with these things because the eye is not as sensitive to the blue light as it is to more red light. So I changed the bulbs out. This is one of the bulbs from my car, and I just went and picked up a ballast. And this originally was one of those 500 watt work lights, and I just gutted it and put this bulb in here. Reflector's not really the right reflector. It gets the job done, but if I turn out all the lights, it actually throws a fair bit of light. As you can see, I've turned out all the other lights in here except for this light, and I'm holding it up over the camera now, and as you can see, that it's got a really nice light. It's a nice even light. So I set this up as a battery powered light, and I just keep a gel cell with it so that if there's a power failure, or if I have to work outside on something, I don't feel like hauling out an extension cord, I just drag this light out, and it's a nice work light, and it stays relatively cool. Not like the 500 watt light that was in it there, where the glass gets so hot that you can't touch it. This thing actually works well. But it's showing that I'm drawing 3 amps from the power supply here. Power supply is not breaking a sweat. If I crank the voltage up, it will probably kill the light. Yeah, about 17 volts. The light actually shuts off, but it'll come back on. Unlike, see, this is the thing with the xenon bulbs. Unlike a mercury lamp or conventional metal halide, they can't restart until they cool down. But these ones, because they start at such a high voltage, you can turn them on and off, and they'll run all day. Anyway, power supply is working great. I wonder what happens if I short circuit the leads together. What will it do? Okay, well, let's short the leads. And it's limited at 5.2 amps. It's not going to hurt it. Try that with some of your other... I would never try that with this other little power supply back here, the buck converter one. It probably wouldn't hurt it, but... because it's got current limiting too, but it doesn't have enough power, I don't think, to start this light up. Just for fun, I'll turn this other power supply on. We'll set the voltage up here. 13 volts. Power on. It's on. Okay. Let's just see whether this one will even strike this light. No. It's lame by comparison, because it just won't do it. Right? I get a little flash out of it. Oh, look, it's even gone into protection. Let's turn it back on. See what happens here. Yeah, nothing. Oh, there, it just shut itself down again. Hey, that's what you get for 20 bucks, right? We'll go back to this one. Anyway, that's the load test here. Let's take a look at some of the other features that this thing has. We'll take a look at the range of the voltage. As we saw, it went down to 0 volts. On the high side, it goes up to 31.79, and I bet you I can get a pretty good spark if I... Oh, it doesn't. It just... little spark, but you see, it's not hurting it. I might weld my probes together here if I'm not careful. But yeah, it seems to be holding up quite well. Let's crack this bad boy open and see how well this thing's put together. So the first thing we're going to do is unplug the power cord from it, and we'll remove the DC banana plugs. Just need a Phillips screwdriver to open this thing up, and I'm curious to see exactly what they're using in here. Is it a linear regulator, or is it a buck converter that they're using for the power regulation? Fan is relatively quiet. It's not that heavy, so I have a feeling this might even be a switching regulator because it doesn't have a lot of weight to it. But we'll find out pretty quick. Is the suspense killing you? Okay, let's take it apart. There it is. And as I thought, it is a switch mode power supply. I could tell that by the weight of it, right? It wasn't really heavy. Actually, it's got 3 transformers in here. And what the heck? Well, that bracket doesn't seem to go anywhere. It's got 2 brackets that are welded down, but this one bracket at the back, which is supposed to be spot welded, this particular one looks like my unit. That spot weld is not done properly. The back bracket. That part's a fail. You can see where it was supposed to be welded. You can see it here. But mine is, the top bracket is not secured. Not that it's going to affect it, because it's not going to go anywhere, right? It's not going to touch up against anything. Although I guess if the board were to in theory move back, it could make contact with the case. So I might want to, I think I probably will. I'll drill this out, and I'm going to put a screw through here just to secure that, so that I don't have to worry about any possible short circuits at some point. But doesn't look to be bad construction. Let's take a look at the board in close detail. So looking at the front side of the board, here's our MOSFETs down here. Probably got 2 diodes here and a MOSFET. Basically what you've got here is you've got your input. Got a main rectifier here, which is going to rectify the incoming AC, and these 2 main filter capacitors, they are rated at 200 volts at 200 microfarads. Now the unit can operate on, it's a dual voltage, so you can operate on 110 or 220. You have to switch it manually though, so it's not an auto switching. So if you're in a 220 country or 240, you'd have to switch it there. For North America, in the 110 position. But you've got your primary side, your oscillator, which is going to be driving these MOSFETs here, and that's going to be going through your main power transformer. And these are going to be, there's 2 more transistors. Here's a diode here, this is a transistor. Q1 and Q2 are down here, and there's another transistor here, Q8. And this is a diode, this is a dual diode over here. So this is your rectifier for the secondary side. And it looks like, from looking at the board, we see here's the transformer here, right? The primary side of the transformer on this side. This is our secondary side. The secondary side of the transformer comes up on these terminals here. As you can see, that is going over to both sides of this rectifier. So these are your AC inputs from the 2 sides of the windings. You're going to have a center tap, so it's a center tapped transformer. So here's our negative terminal here, going over to here. This is going to be an inductor, it looks like. And the other side here is going over to the 2 inputs to the diode, and then they're feeding into this linear. This is a linear, looks like a linear regulator. No? What do we got here? I'm looking on the screen here to see how it's hooked up. Yes. So this is the base here, which is coming in from the top side of the board over here. This is your feedback loop. This is a linear regulator on this thing. It's not. It's not a switch mode. It's a switch mode power supply, but it's not. It's not a buck converter as I thought it was going to be. It looks like it's a linear regulator, because here is the output from the diode, and it's going directly into the transistor here, and then it's coming out, going this way, and this goes through a shunt there, and that goes to the positive lead. So you got your current shunt across here. This is a current shunt. So here's these capacitors here. These are our DC filter caps. They're 1000 microfarad at 35 volts. So they are what's filtering the output from this regulator here. If you look at the diode block, the two outside pins here are the inputs right from the transformer, and then it's coming out from the output here. A positive terminal here is going into this transistor, and it's also going in parallel with these two filter capacitors. So these are our main filters. Our negative side of the transformer here goes into this inductor on this side. Zoom the camera out a bit so you guys can see what I'm doing. So the negative side of the transformer, or the common, I should say, the center tap, is going into this inductor here. The inductor is connected across these terminals. Here's the inductor I'm talking about here. It's a toroidal inductor, and that is going to the negative terminal of the filter capacitors. The other sides of the winding, the two main windings with respect to the center tap, are the ones that are going through the rectifier diode, and they are connected directly to these capacitors here, and they're also connected into the, I'm going to say it's probably the collector. It's probably base collector emitter on this basing. I haven't looked up the transistor, but it's probably BCE. So I'm going to say the collector. The emitter is going along here. It's connected to this capacitor, the positive terminal of it. It also goes into, this is the current shunt here. This is for your current loop, for measuring the current for the, so it knows the voltage drop across here. And this is for the current loop, and you can see it connected right here directly to the positive terminal here. The negative terminal here is also, there's another filter capacitor here on the other side of the shunt. So the output comes through here, positive, goes through the shunt to this capacitor, positive terminal to the positive terminal here, feeding out to the outside world. Here is our voltage control down in here. And our circuitry that's going to control that is going to be these ICs here, is going to be the voltage and the current control. And your current sense loop is going to be in through here, and probably in through some of these other circuits as well in here. So I'm going to measure with the scope the base drive and verify that if it's a signal, if it's a DC signal or it's a PWM, and it's actually a DC signal. And I'll show you guys here on the scope. Now you'll have to ignore that noise you see on the scope. That's actually not noise, okay? That is signal that's being picked up because I have my little 400 milliwatt AM transmitter turned on, and I'm actually picking up signal from that. My scope is that sensitive. Okay, I'm scoping the base for this regulator transistor, and as I bring up the voltage, you'll see that it actually just goes up. This is the base drive. I should turn off that measurement. Let's turn that cursor off here. Where are we here? Cursor. Get that off the screen. Okay, now we can measure the voltage. as you can see, as I turn it up, it'll go up to 34 volts. This is the base drive, right? If I look at the collector is going to go up and down with it as well. And if I go over to this one here, now what I want to know is, does this actually change the output from the chopper transformer, or is it always running? So this is the AC. Okay. So now we get a little more insight as to how this thing works. When I adjust the voltage on this thing, this is what's coming off of the transformer. Right? This is the transformer. This is what's going into the diode here. This is that dual diode. Here's the output of it. It's going to have a DC voltage on it. And here's the transformer. Here's the AC side. Right? So if we look at the actual transformer itself, I'm now scoping the actual transformer right here. Right? I'm going to scope. I was looking at so it's actually not, it has a linear regulator on here, but it's actually controlling the voltage on the actual transformer itself. If I measure here on the transformer, there's nothing right now on the scope. If we go back over to the scope here, you'll see that there's nothing on the scope. But as I ramp up the DC power, the transformer starts to come to life. So it's actually changing the duty cycle of the actual oscillator. If I look at the AC side, right, this is the AC side of the transformer itself, the transformer winding, the primary side. So if I look at the actual MOSFET itself, this is the, now I wouldn't advise anybody sticking their probe in here because this is going to have mains power. I'm on an isolation transformer now, by the way, now, but this is the this is going to be the drive from the actual MOSFETs themselves. So what I was just looking at, that is I was actually looking at these MOSFET transistors right here. So it's actually changing the duty cycle to the transformer, and that's one of the ways that they're regulating the voltage on this. So this entire transformer is it's changing, or they're changing the frequency, and they're changing the duty cycle of the MOSFETs on the transformer itself, which is, I didn't expect to see a design like that. I figured for sure this was just going to be a fixed frequency and it was going to regulate using a linear regulator. They are using a linear regulator. This is to smooth out any of the noise and stuff that's generated, but they're actually using the other circuits in here, using these other transformers. We're actually changing the switching duty cycle and the switching frequency going into the main transformer, and that's how they change the voltage, is they change the frequency, which makes the transformer more or less efficient. They take it in or out of resonance, and that's how all switch mode power supplies work anyway, right? All the regulated switch mode power supplies, you have a feedback loop that controls the oscillator frequency, and you raise or lower the oscillator frequency accordingly to change your output voltage. This is taking it one step further. Yes, you've got all the same circuitry in here, and here's the optocoupler right down here, right, for the feedback loop. There's your optocoupler, but in this case, we are actually able to change the frequency or change the voltage with our controls, and they're doing it by changing the actual oscillator operating frequency to the actual MOSFETs, to the input of this. So that's where our course adjustment is taking place, and then our linear regulator here is not actually doing much in the way of regulation as far as the voltage goes. It is more along the lines of, this is the current limiter, and this is the filtering, the last filtering stage to take out ripple. This is what's going to limit the amount of current. When you go over on the current, this is what's going to shut down the output. We can prove this theory. I've got my scope now. I'm monitoring the base to this current regulator transistor, and watch what happens when I short. You see, when I short the output terminals, I've got the current limited down to like 1 amp. When I short it, you'll see that it drops down, but it's still trying to put out, it's limiting the current. Normally it's wide open, but the voltage is going to drop down here. This is going to limit the current. See, it's not going to 0. But when I release the short, you can see the action it takes there as it's going back up. Now by comparison, if I scope the output that's going to the voltage terminal, you'll see that it goes, when I short it, it goes right to 0 because I'm providing a dead short. And if I look at the input side of it, it will actually shut down a second later. So when I short it, it takes a little bit of time before it shuts down, because what it's doing is it's actually shutting down the main power supply when I short it, you see? So it's going into protective shutdown, and it's shutting the whole power supply down once the current is exceeded. So what I was doing there, those tests that I was making, I was testing it here on the base drive, and the base drive was continuing to operate when it was into an overcurrent situation. As soon as I shorted it, the rail going to the output, which is this one here, would go immediately to ground. The input here was delayed slightly before it shut off, and it shut off when the main power supply shut off. The reason you've got these other transformers down here is these ones here are separate power supplies to operate the sensing circuit. So you've got another switching regulator down here. That's probably the MOSFET the MOSFET regulator here for that. This 8-pin dip. This is likely the MOSFET for one of these power supplies here. And it's got its own set of capacitors down here as well, and it's got its own diodes in here. This is what's operating this circuitry. So even when the main power supply is shut down from an overload, because here's your main power supply here, the rest of the power supply that operates the logic, that operates the display and operates the circuitry, it is isolated and it continues to operate. So if you overload, the circuitry actually, first of all, limits the current here through this transistor, and if you overload it and go beyond the maximum limit, it's going to shut the power supply down and limit it. So that's actually not a bad design on this this power supply. And I haven't worked on one of these. I haven't had one of these before. Power supplies I've had in the past have all been just linear regulation with a big transformer, but this is actually kind of a smart way of doing it. Construction-wise, looks to be pretty good. I don't know if these big solder connections here are as good as I'd like to see them, but look a little bit flaky, but you know, might want to touch those up before I put it together. I might just go over at least these big ones here. It doesn't look bad though, but definitely I'm going to take that and address that before I put it back together. Maybe drill a hole through here and just put a self-tapping screw. It's got a tab on the back here where it was supposed to be spot welded, so I can probably drill through the back and drill through that tab and just put a self-tapping screw in there, and that'll fix that up. But other than that, hey, I see nothing wrong with this design. You might want to check that out at the manufacturing level. Maybe it's just this one, but yeah, it doesn't look to be too bad. It looks to be actually pretty good for what the cost is on this thing. They're not that expensive. Nice little bench power supply. I think I'm going to get a lot of use out of this thing. Okay, that's it. That's a quick look at the Pevono PS305H power supply. And if you like these videos, consider making a contribution either through PayPal or through Patreon. It's through your support that I can do things like buy these, because I actually purchased this at retail off of Amazon, and the link to this will be up on the channel. And you know, if you like these videos, keep them coming. That's through donations that I get from my subscribers that allow me to go out and buy these things. I've got something really cool coming. I'm not going to tell you what it is because I don't know when you're watching this, but I've got a real cool piece of equipment that is on its way that was made possible through donations from my viewers, and I thank all of you. Until the next time, we'll catch you again real soon. Bye for now.